Okay, this is lesson 10 for 8th grade, and we're talking rational numbers and equivalent fractions today. So, before we jump into what this is, let's build up to what a rational number is. Excuse me, and then we can eventually get to equivalent fractions. Alright, introduction to rationals. So in mathematics there are many types of numbers, and they all fall into different categories. Some of them fall into multiple categories, as we'll find out. Alright, this loop over here, this is a set of whole numbers. We've talked about these before. They go from 0 all the way to positive infinity, and they're all whole. They're all very nice numbers, easy to work with. Okay. Now, first question. If we add any two whole numbers, is the sum going to be a whole number? Well, if we take any of these numbers up to infinity and we add two of them, yes, we will get another whole number. How about if we multiply any two whole numbers? Well, if we multiply any two whole numbers, yes, we'll still get a whole number. Even if we multiply by 0, we'll get 0, and that is a whole number. So, in this sense, we say that we will get a whole number by adding two or by multiplying two whole numbers together. So we say that whole numbers are closed under addition and multiplication. So they are closed. That's the term that we use there. But what about subtraction? Are the whole numbers closed under subtraction? That is to say, if we subtract two whole numbers, will the difference also be a whole number? Turns out that if we subtract two whole numbers, we will not always get a whole number. So, if we subtract two a whole, certainly it says that 3 minus 1 is a whole number, but if we reverse that, 1 minus 3 is negative 2. And negative 2 is not a whole number. So, now we're introducing negative numbers. Okay, integers are numbers that contain all the whole numbers, so integers are whole numbers, whole numbers are integers are not always whole numbers. So integers contain all the whole numbers, but they also contain all the negative numbers. So if I wrote that as a set, the integers would be, let's see, negative 2, negative 1, 0, 1, 2. Alright, so integers go from 0 to negative infinity, but also from 0 to positive infinity. So, yes, they contain the whole numbers, but they also contain all the negative numbers. Notice that there are no fractions in here. The set of integers is closed under addition, multiplication, and subtraction. So if we add, multiply, or subtract any two integers, we will still get an integer. But what happens if we divide two integers? Are we going to get an integer every time? The answer is no, because we could do, let's just take two positive ones and we'll make them easy. 1 divided by 4. That is not 4, by the way. 4 divided by 1 equals 4. 1 divided by 4, if you type that into your calculator, you're going to get 0.25. Now remember, there are different notations for division, so you could also write it like this. 1 divided by 4 is the same as 1/4. 1 divided by 4, because that bar means division. So, now we've got fractions involved, and none of the integers contain fractions. So, no, it is not closed under division, but it is closed under addition, multiplication, and subtraction. So, now we've got fractions, and yes, you can have negative fractions as well. And that's where the rationals come into play, rational numbers. Now, the thing that we want to point out here, rationals, is this word right here, ratio. Ratio always means we're dealing with fractions. That's how we can remember what the rational numbers are. They contain integers, they contain whole numbers, and they contain fractions. So rationals are the largest set of numbers that we've talked about so far. They, since we can write any whole number or integer as a fraction, I could take -2 here. I can write that as a fraction. -2 is the same thing as -2 over 1, and that's a fraction. I could take 4 over 1, that's a fraction. So that's why the rational numbers contain these two sets of numbers as well. And just remember that you can have a negative fraction as well, which I will show you right now, I believe. Alright, so if we have a number line here, these are all rationals, and some of them are more than one thing. This is an integer, it's a rational. This is an integer, it's a rational, and it's a whole number. So you can have numbers that are part of more than one group or one set. So if we look at our number line here, -5 over 3 falls right here. This is -1/2, and 1/2, 3/2, 7/3. All of those are rational numbers. Actually, every number up here is a rational number. Okay? So where do we need this? Well, it's when we decide which numbers fall into which category. So if we look at -3 here, it says decide whether it's a whole number, an integer, or a rational number. So write every one that applies, then sketch it on the number line. I'm not going to take the time to sketch it on the number line, but what you would do is if we took -3, we'd put it right here. That's all you have to do. -3, is that a whole number? No, it's not, because whole numbers are not negative. So it's not whole. Is it an integer? Yes, it is an integer. Negatives are integers. How about a rational number? Well, we do have, remember, -3 can be written as -3 over 1, which is a fraction. And just to remind you that rationals contain whole numbers and integers. So if it's an integer, it's going to be a rational. Alright. 2. Is 2 a whole number? It's positive and it's a counting number. So we have a whole number. If it's a whole number, it's going to be an integer. And if it's a whole number, it's also going to be a rational. So this one's all 3. So integer as well, and rational. So there you go. That one's a positive whole number is going to be all 3. A negative number is going to be integer and rational. And C, is C a whole number? No, because we have a fraction. Is it an integer? No, because we have a fraction. Is it a rational? Yes. So this one is only 1. So, something to note. Just because you know it's part of one group, make sure you check the other groups too, because it might be a part of something else. Check my time here quick. Alright, we're doing okay. Okay, now we can talk equivalent fractions. And these the students have seen before. This is 1/2 if we look at it in a circle. 1/2 of the circle shaded. That is the same case in all of these, except for the difference is we have different equal parts. So this is 1 out of 2, this is 2 out of 4, 3 out of 6, 4 out of 8. Now these are what we call equivalent fractions. They are the same thing as 1/2, but they're written a different way. Okay, where these come in handy. Yes, we know that they are equivalent because they all reduce to the same fraction. We reduce them by finding common factors between the numerator and the denominator. So, for instance, if we take 16 and 20, here are all the factors of 16, here are all the factors of 20. And you don't have to go through and do this every time, but this helps just to visualize. And remember, we used to make these rainbow things. 1 times 16 gives you 16, 2 times 8 gives you 16, 4 times 4 gives you 16, 1 times 20 gives you 20, 2 times 10 gives you 20, 4 times 5 gives you 20. Okay, so what I did is I rewrote 16 as 4 times 4, and I rewrote 20 as 4 times 5. Well, we have two things being multiplied up here, two things being multiplied down here. We can do this to reduce, and we're left with 4 over 5, okay? And actually what we used here, we used the greatest common factor between 16 and 20 to reduce our fraction. If you do use the greatest common factor, it's going to reduce to its simplest form right away. So it's kind of nice to know what the greatest common factor is, or the GCF as we call it, because then you know once you find that, it'll reduce to simplest terms. We could have divided each of these by 2. We could have done 2, and we would have got 8 over 10, but then we weren't done yet. We would have had to divide by 2 again to get 4 and 5, so 4/5. So there are multiple ways to do it, but finding the GCF, if you happen to, will save you some time. Okay, now this fraction says, or this problem says, use the prime factorization to reduce 72 over 108. I'm not a big stickler on this. If you can reduce the fraction, that's all I'm concerned about. But if we were to do the prime factorization, this is what it would look like. 72, this is the prime factorization of it. 2 times 2 times 2 times 3 times 3. If you multiplied all those together, you get 72. It's called the prime factorization because these are all prime numbers that factor into 72. 108 has 2 times 2 times 3 times 3 times 3. And then what you see that they do here is they're crossing out 2's, and they're putting little 1's here. The reason they're doing that is because 2 over 2 is 1, 2 over 2 is 1, 3 over 3 is 1, 3 over 3 is 1. That's the reason we can do it. Everything's being multiplied, so everything's being multiplied on top, everything's being multiplied on bottom, and this line again means division. So we're just kind of canceling out. So basically what they did is they took pairs, 2's and 3's, and you're left with 2/3. So that's one way you can reduce. I'm not a big stickler on how you want to reduce. That's just one way you can do it. Alright. We can form equivalent fractions by multiplying a fraction by a fraction equal to 1. Where this is going to come in handy is when we're trying to find common denominators. So these are all 1. We can see 2 over 2, 3 over 3, 4 over 4. If we take 1/2 times 2 over 2, we get 2 over 4. If we take 1/2 times 3 over 3, we get 3 over 6. 1/2 times 4 over 4, we get 4 over 8. So, what property of multiplication are we using when we multiply a fraction equal to 1? We learned earlier that when we multiply by 1, nothing changes. We called that the multiplicative identity. And that's true because 1/2 and 2/4 are the same thing, and we multiplied by 1, so nothing really changed. So, check my time quick. Alright, we're getting there. So I'm going to quickly finish here. Write a fraction equivalent to 1/2 that has a denominator of 40. So we need 1/2 equal to 40. Well, 2 times 20 will get us to 40. So we'll do 1 times 20, and there we go. We get 20 over 40. Same thing as 1/2. That's an equivalent fraction. And if we wanted to compare these two real quick, we would want to find a common denominator. Common denominator would be 15. So 2 over 3 times 5 will give us 10 over 15, and 3 over 5 times 3 over 3 will give us 9 over 15. So which one's bigger? 10 over 15 is bigger than 9 over 15, so 2/3. Alright, my time's running out. That was lesson 10 for 8th grade.